And remember, your final in here is cumulative. But if you're studying your tests and your quizzes, you shouldn't have a problem. Okay, so let's finish chapter 9, which is our bonding theory. And we started talking about resonance structures. And resonance structures happen when we can have multiple ways that electrons can be in our molecule, where the positions are. And we typically show them as two separate structures so we can understand them. But in reality, the molecule doesn't exist as two separate structures, but an average of the structures. But there are some rules that we have to follow for drawing resonance structures. And we're just going to really touch on this today. If you take organic chemistry, you're really going to be looking at this. It's very relevant. And we spend a couple of days working with this. So first off, resonance structures must have the same connectivity, because if the connectivity is different, then it's not a resonance structure, it's a whole different molecule. So a different molecule is going to have different physical properties, different reactivity. These two things that we're seeing are two different molecules. We have ethanol, you might recognize it, it's the alcohol that's often in what we drink, versus methyl ether, which you do not want to be drinking then. It would not be good for you. So those two things are not resonance structures. They are isomers with different connectivity. The other thing is our resonance structures must have the same amount of electrons. If they don't have the same amount of electrons, they're not resonance structures. They're two different compounds. So resonance structures have to have the same electrons. This is just our same thing that we are always talking about with Lewis structures, in that hydrogen doesn't exceed its duet, and anything in the second row can't exceed an octet, so that's important. Your resonance structures shouldn't break those rules, but that's the same rules for Lewis structures. If you're talking while I'm talking, you can come teach the class. Okay, and then lastly, resonance structures must have overall the same overall charge. Now, the individual atoms in the resonance structure might have a different charge, but overall, the charge should be the same, because the overall charge is based on the amount of electrons, and the amount of electrons doesn't change. So the overall charge is always going to be the same, even though you might have different charge species. So let's look at an example. Not only do they have to follow those rules, but sometimes some resonance structures can be drawn and they're not good resonance structures. And by good resonance structures, what we mean is they're just too unstable to exist and they don't contribute to the overall average structure. So we're not deciding that they're good or bad based on just us saying it's good or bad, but based on what we see experimentally, that these structures don't contribute to the overall structure. So if we're looking at this particular compound here, which is acetic acid, that's vinegar. If we look at acetic acid does have a resonance structure, but I'm showing two resonance structures shown here. Better resonance structures contain full octets. The most contributing resonance structure is going to contain a full octet, and usually that wins over other things. Better resonance structures have fewer formal charges. A formal charge in an atom means that the atom isn't very stable. They can exist, but an atom is most stable when it's neutral. So, especially when we're talking about covalently bonding. So if we look at acetic acid, this is going to be our best resonance structure because all atoms have an octet and we don't have any formal charge. And that is going to be our most contributing resonance structure, and our average resonance structure will look the most like that. But this resonance structure that's next to it is also an acceptable contributing resonance structure. But we do have formal charges, so it's just not as stable as this one. Better structures have smaller formal charges. For a lot of our compounds, especially oxygen, nitrogen, carbon, and our halogens, we won't typically see anything more than a +1 or a -1 charge, because the more unbalanced that charge away from the valence that's predicted by the periodic table, the less stable. So every once in a while you might see a nitrogen with a 2 plus or something else, but typically you won't see anything more than -1 or +1. So if you see multiple atoms that have charges in the molecule, or let's say a +3, that's probably unlikely to exist because it's too unstable, it's too deviating away from the valence it should have. So we don't see that a lot. And lastly, better structures have the negative formal charge on the more electronegative atom. Electronegativity is just a measure in how much that atom attracts electrons to itself. If an atom is more electronegative, it wants to have electrons closer to it. So the least amount of electrons it has, the less stable it is. So if we look at this structure, everything's neutral, we're all good. So this is our most contributing, and it's very stable. So this is a viable resonance structure. Here, we do have formal charges, but it's still a viable resonance structure because we have the negative charge on the oxygen, and the oxygen is the more electronegative. Now, carbon doesn't have a complete octet. That doesn't mean it can't exist, and it does exist, but it's not as stable as our first structure. Now, the last structure is not really a good resonance structure. We do have the same amount of total electrons, we do have the same total charge, so we're not breaking any rules, but carbon isn't very stable with a negative charge, and oxygen isn't very stable with a positive charge, because oxygen is more electronegative. So it wants that negative charge. So actually, this particular resonance structure is negligible. And by negligible, we mean we don't experimentally see it contributing to the overall structure. Now, there is an exception. Oxygen can have a positive charge if it has a full octet, but oxygen doesn't have a full octet here. So an electronegative atom can carry a positive charge, but it will typically have a full octet. If it doesn't, it's usually too unstable. So that's what we mean by better. Now, I do want to point out some things as far as our rules between these two. Even though we don't have any formal charges here, and we do have formal charges here, our overall charge is the same for both of those because we have the same number of electrons. So this overall charge is 0. This has a positive one and a negative one. Its overall charge is still 0. So we still have the same amount of electrons. We still have the same connectivity of our atoms. But the difference between these two is that here we have this double bond between the carbon and oxygen. Here, the oxygen only has the electrons. We don't have the double bond. So it's just how the electrons are shared. So those are viable resonance structures. The third one's not a great one because the carbon shouldn't have a negative charge. The oxygen doesn't have a complete octet and it has a positive charge. So not very stable. So when you're drawing resonance structures, first draw your Lewis structure that's going to minimize or maximize your octets, meaning all of your atoms have an octet. So we already looked at this particular one. Then assign formal charges because you always want to show your formal charges on a Lewis structure. So there's our formal charges there. Then we can move our lone pairs towards our more electropositive atom. And if we do that and put a double bond between nitrogen and oxygen, remember nitrogen can't have more than 8 electrons. So then our nitrogen would have 10 electrons, and that's not allowed because nitrogen's in the second row. So we just have to move that other double bond. And that resulting compound with our formal charges are drawn. There's actually one more resonance structure if I were to label those oxygens A, B, and C. And the other resonance structure would be the double bond between that third oxygen. These are actually all equal resonance structures because they all have the negative charge on the oxygen, they all have the positive charge on the nitrogen. Again, overall, we have a -1 charge for all of the structures, all of our resonance structures. So there is one more resonance structure for this particular one, and it's a double bond between oxygen B and nitrogen. So this one actually has 3. So this is fully how to do our Lewis structures, and then the last thing is to determine if there's any resonance structures. And that'll be really important when you take organic chemistry, so we're not going to focus on this anymore. This is just an introduction, and I really recommend going through these slides before you start organic chemistry, because you're going to get into way more details with this in organic chemistry. So this is just an introduction. Now there are some exceptions to the octet rule that I did want to go through for drawing Lewis structures. One is free radicals. We're not going to talk too much about this, just a quick slide on it. You'll look more at this later. Free radicals are when we have, instead of a lone pair, an unpaired electron. And they're usually pretty unstable. One example, NO can have a free radical in the nitrogen. Now notice that nitrogen here doesn't necessarily have a complete octet, but it doesn't have a formal charge. So our free radicals typically don't have that complete octet, so we have a good bit of reactivity. Our radicals are typically pretty reactive. But we don't actually have a formal charge. If you calculate the formal charge for that nitrogen, it is 0. So it doesn't have the instability of having a charge, but it doesn't have an octet, and it wants to, so they're typically pretty reactive. And of course, that NO can react with oxygen, it can react with ozone, and it's a big pollutant because of that, because of its reactivity. Radical reactions are pretty important. The actual combustion process is actually a radical process, and that's not really what we're going to go over too much in this class. There's also a lot of the plastics that you use in everyday life, your desks, things like that, or polymerized through a radical polymerization reaction. Which again, we're not going to get into more detail about that in this class, but I do, and I have taught a polymer chemistry class where we get into things like radical reactions for polymer chemistry. So we're not going to get more into that, but that is, of course, an exception to the octet rule. And radicals do exist, and they are pretty important that we know about them. You've probably heard about free radicals when you think about food spoiling, and a lot of times additives in food to keep food from spoiling too fast, or additives that will basically stop the radical process that causes food to spoil by sucking up radicals. So you might hear terms like that, like free radicals, and it's also theorized that aging is a radical process, but there's actually not that much data to show that. But you'll often see things in skincare products that claim to stop the radical process of aging, like some vitamins. But again, there's not that much science behind that concept. Another exception are things like boron. If boron bonds with fluorine, it doesn't form an octet. Because again, if we look at the Lewis structure of boron, it actually predicts that it would only form 3 single bonds because we only have those 3 valence electrons, but it's still not very stable because boron doesn't have an octet. So the question you might ask yourself is, why doesn't it form a double bond with fluorine? And the reason why is, if we look at the formal charges, that would give our more electropositive atom, boron, a negative charge, and our very electronegative fluorine a positive charge. And that's really unlikely. So it's unlikely it exists like this, and its Lewis structure is actually this structure, even though it only has 6 electrons. The last example of exceptions are expanded octets, things like arsenic and sulfur. Anything 3 and under can have expanded octets because they're so close to the d orbitals, so they have more space for electrons to go in. So for example, we could have an SF6 compound where sulfur actually has 12 electrons surrounding it. And here this arsenic can have these 5 fluorines. So they do have an expanded octet. Never, though, any of our atoms in our second row, because they don't have d orbitals close enough to them to be able to do this. Now that we know how to draw Lewis structures, there's 2 more things we're going to discuss to end this chapter. One is a little bit about bond length and bond strength. So as far as bond length, it makes sense that as we go down the periodic table, our atoms get bigger, so the length between our nuclei, which is usually what we're looking at, is going to get bigger. That just makes sense because our atoms are bigger. So there's a couple of ways to determine bond length. Typically what we describe as average bond length, because there are different types of measurements. So just recognize this. You might see a number that's slightly different than the picometers shown here, but what we're usually representing is an average bond length. So as we go down the periodic table, the bond length gets longer because the two atoms are further apart. But let's look at some other trends. The more electrons two atoms share, typically the shorter the covalent bond. So what does that mean? That means triple bonds are shorter than double bonds, and double bonds are shorter than single bonds. And this is showing a carbon-carbon triple bond. This isn't showing all the bonds to that carbon. This is just focusing on the bond. So just keep that in mind. Carbon does typically form 4 bonds. I'm not showing all the bonds in these. So typically a triple bond is much shorter than a carbon-carbon single bond. There's more to this than just the amount of electrons shared. And you're going to get to that in chapter 10, but for right now, the more bonds shared, the shorter the bond. If we compare carbon-nitrogen triple, double, and single bonds, we see the same trend. That we do have a shorter bond when we share more electrons. And there's a bit more to the explanation for this that I'm not going to go into right now. Also, our bond length decreases from left to right across the periodic table because more electronegative atoms pull electrons towards them, therefore shortening the bond. Now remember, as we go across the periodic table, though the atom size gets smaller, that's not really the contributing factor. It's not a huge difference like it is going down. What we're more looking at is, as you have more electronegative atoms, it's going to shorten the bond because they pull the electrons closer to themselves. So if we compare our carbon-carbon bond, where carbon's the same throughout, so let's just compare the second atom. Carbon is the least electronegative, so we have the longer bond. Nitrogen's more electronegative, so the bond gets a bit shorter. Oxygen's even more electronegative, so the bond's even shorter. Is it a huge difference? Not necessarily. The difference isn't huge, but it is a significant difference. And of course, the easy one, as we go down the column, the bond length has to get bigger because the atoms are bigger. So that one's just really easy. Comparing our fluorine-fluorine bond, our chlorine-chlorine bond, and our bromine-bromine bond. In general, the longer the bond, the less the electrons are being tightly shared, so they're usually easier to break. And there's a little bit more to that as well, but that's in general. So what does that mean? Single bonds are easier to break than double bonds because it's a longer bond. So that brings us to the concept of bond energies. In a covalent reaction especially, what we're doing is breaking covalent bonds and forming new covalent bonds. That's what we do in a reaction. So we can predict our delta H, bringing that back to thermodynamics, if we know how much energy it takes to break those covalent bonds. So we can actually calculate our delta H of reaction by comparing how much energy it costs to break a bond versus the profit from making a new bond. Breaking a bond always takes energy. Making a bond is always going to release energy. If it's taking energy, what sign is that heat going to be? Taking it into the system. So the system's going to be positive. It's taking energy. And when we form a bond, it's releasing energy. So what's that going to do to our delta H? Negative. So keep that in mind. That's really important for what we're going to do. This is just a bunch of addition and subtraction. But that's the key there, is making bonds takes energy, so that's positive, and breaking bonds releases energy. I just said that wrong. I'm so sorry. Breaking bonds take energy because it's stable when it has that octet and it's sharing electrons. So that's why making them release energy, we're forming a more stable thing. Now remember, for a reaction to be favored in the forward direction, the overall delta H has to be negative, meaning our product should be more stable than our starting materials. So that's what we're looking at. Now, the bond energies that I'm going to show you are measured in the gas state and measured as if the bonds were breaking homolytically. And that can give us a good idea of our delta H of our reaction, but there are a couple of limitations with this. One, most of our organic covalent chemical reactions are not done in the gas phase, they're done in the presence of solvent. Because most of them are solids at room temperature or liquids at room temperature. So that's one thing to keep in mind. This isn't, the gas phase is nice because we don't have effects from the solvents, which solvents can help stabilize our reactions or make our reactions slower depending on the solvents we choose. So that's one thing, is that this number might not be exact for what you do in the lab because we don't typically do gas phase reactions in the lab. And two, most of our organic chemistry reactions are not homolytic bond cleavage, but heterolytic bond cleavage, where both of the electrons go towards the more electronegative atom when we break a bond. But it's still a good way to predict your delta H. So just keep that in mind. So as far as our trends in bond energies, before I show you the numbers, like I said, the longer the bond, typically the easier it is to break. So we see that triple bonds being shorter take more energy to break. Now a note for this, when I'm comparing breaking the triple bond versus a double versus a single, I am comparing fully breaking the bond between the two carbons. It is easier to break one of these triple bonds, but when we're talking about this is the total energy to break all three. So of course it takes more energy to break 3 bonds than it takes to break 1 bond. And we're not going to go more into detail with that, but later on it's going to be important. Not in this class, but later on classes. So just keep that in mind. What we're talking about is fully breaking all 3 bonds takes more energy than breaking only 2 bonds, which takes more energy than breaking only 1 bond. We see the same trends in our carbon-nitrogen triple bonds. Also, we see trends that the shorter the covalent bond, the shorter the bond, the stronger it's going to be. So fluorine's smaller than chlorine, so therefore we have a shorter bond, so it takes more energy to break. Bonds get weaker going down a column because it's a longer bond, so it's easier to break a bromine-bromine bond than a chlorine-chlorine bond because bromine's bigger. We often use our average bond energies to estimate our overall delta H of our reaction. Now this, as far as the numbers, is easier to measure in the gas phase, but again, typically in the lab you're not doing it in the gas phase. So bond breaking is endothermic and it takes energy. Bond making a new bond, is exothermic and it gives off energy. So the numbers, the magnitude, is going to be the same if we're talking about forming a carbon-carbon single bond or breaking a carbon-carbon single bond. The difference is going to be the sign. So when you are going to be doing this, you're going to have a list of numbers, but you're going to have to put in the positive or negative sign depending on whether the bond is breaking or forming. Another thing to note is our overall energy of our reactants. We don't show the energy of reactant 1 and reactant 2. We show the energy of both of our reactants and both of our products. So notice we only have one energy, and that's the energy of our reactants total and our energy of our products. We're going to make 6 products, that's all of the products. So it's one thing to note. And we can then calculate our total delta H of our reaction by just adding the amount of energy it takes to break our bonds in our starting material plus the amount of energy given off when our bonds are formed in our product. So it's very straightforward. It's just an overall addition or subtraction. The key is to know where to put the sign. And then of course remember, for a reaction to be spontaneous, it must be our products are lower in energy than our reactants, so our overall delta H would be negative. So let's look at some examples. You don't need to memorize these numbers. You should be able to pick out a trend if I gave you 3 bonds and I asked you which one's the strongest. But I won't ask you to predict the numbers. You don't have to predict the magnitudes, that would be given to you. So let's look at this example. We're going to predict the delta H of this reaction. The first step is figuring out what bonds are being broken in the starting material and what bonds are being formed in the products. Bless you. So we're not touching 3 of the carbon-hydrogen bonds. They're staying the same, so we're not going to be even looking at them. Instead, we're breaking this carbon-hydrogen bond, and we also have to break the chlorine-chlorine bond. We're forming a carbon-chlorine bond, and we're forming a hydrogen-chlorine bond. So that's what we're doing. Remember, in blue, breaking takes energy, so what we're going to do is find a carbon-hydrogen single bond in this chart, and we're going to find the number, and the chlorine-chlorine single bond in the chart. We're going to find the number. Again, I'll give you the chart. You don't need to memorize the numbers. In the chart, the numbers don't contain a sign. You have to put that in. So we're looking at breaking them, so that sign's going to be positive. That takes energy. So overall, it's going to take 657 kilojoules of energy to break my carbon-hydrogen bond and my chlorine-chlorine bond. Then we're forming a carbon-chlorine bond, so I find that. And we're also forming a hydrogen-chlorine bond. So I find those two. We're forming those, so those will be negative. So total, we're forming negative 770 kilojoules. Now my overall delta H is going to be this plus this. And I already can tell you it's going to be an exothermic process because I'm giving off more energy than I'm taking. So 657 plus my negative 770 is going to give me my overall delta H of negative 113 kilojoules. So it's just adding and subtracting, but you do need to know when to put the positive sign and when to put the negative sign. What this is representing is it took 657 kilojoules of energy to break those bonds to form these high energy structures, we call that our intermediates. And then to form the bonds for the product, it took negative 770. So my delta H is the difference here. And that is, of course, that negative 113. And as you can see, your products are lower in energy. Let's look at another example. Now here we have an oxygen-oxygen double bond. So we are breaking the hydrogen-hydrogen bond, and we're breaking 1 mole of oxygen-oxygen double bond. So we want to choose the oxygen-oxygen double bond, not the oxygen-oxygen single bond energy. That's key. It takes more energy to break a double bond, so we need to use the right one. So that's going to be a total of 934 kilojoules. Now note, we are forming 1 oxygen-oxygen single bond, but we're forming 2 oxygen-hydrogen single bonds. So we take that 464, well, we can multiply it by 2 because we're forming 2 of them. Then adding that together, and then our difference is going to be plus 934 plus our minus 1070. So again, this one's an exothermic reaction at minus 136 kilojoules. Again, you will be given a chart. I don't expect you to memorize those. That's silly. The actual appendix delta H of formation, meaning what was observed experimentally, is very close to what we just figured out. So that shows that this works. I want to go through one more example of this. And this one I really wanted to go through because this one has our coefficients, and you have to take that into account. This tells me that I take 2 moles of this C2H2 molecule with 5 moles of O2. I have to take those coefficients into account when I'm calculating this. So that's why I'm showing this one. And this is more what you'll see on your test because I'm not going to give you a big chart. So this might have more than what you need in it. And also note that my carbon-oxygen double bond in CO2 is a bit different of a carbon-oxygen double bond because CO2 is the only one where carbon is double bonded to 2 oxygens. So it's quite a different one, and it does have a different bond energy. Actually, a hugely different bond energy. CO2 is pretty stable. So when we're looking at this one, again, same concept, but we're fully breaking this carbon-carbon triple bond, and we're breaking 2 carbon-hydrogen bonds. And we're also breaking our oxygen-oxygen double bond, and then we're forming those. So we're breaking 2 of these hydrogens. So I'm going to write them both down. I'm just writing them separately. And also 1 carbon-carbon triple bond. And I'm writing them like this because I want to take into account those coefficients. And also my oxygen-oxygen double bond. That's not CO2, so that one's that one. And remember, forming bonds is going to give up energy. Now what I'm not taking into account with these numbers, if I just add them together, it's not going to give me the right answer because I'm not taking into account the coefficients. So I need to take into account the coefficients. So I'm writing the CH bonds 2 separate times just so I'm following it correctly. But we have a 2 here, so I'm going to put a 2 in front of all of those. And then for my O2, we have a 5. So I'm going to put a 5 there. So actually, my total amount of energy it takes for this reaction is plus 5,820. And then the same thing for my products. I have to take the 4 and that 2 coefficients into account. So I am. And then that gives me an overall negative 8,248. So again, if there's coefficients, they have to be taken into account. Because that means it took 2 molecules of C2H2 to react with 5 molecules of O2. So in that reaction, we're not just breaking 1 O2 bond, we're breaking 5 O2 bonds. Then we just add it together and we get our overall energy. So that's it for our covalent bonds. The last little thing we're going to talk about in this chapter, and we're not going to spend much time on it, is metallic bonds, meaning our metals, especially this is typically metals, either our elemental, so sodium, all of our metals when they're in their elemental form are actually here, not when they're ions, so sodium metal, potassium metal. And then, so this is really our elemental form of all of our metal atoms. And they do exist in what we call a metallic bond, because they don't just exist on their own. So what do they look like? Well, sodium doesn't want its electron. It really doesn't. So instead, what we form when sodium makes sodium metal is a bunch of sodium pluses with their electrons just hanging around near them. And that's what we call metallic bonds. And our sodium metal is pretty reactive. But our other metals, things like gold, things like copper, they're stable in their metallic bonds. But our first and second row of group are pretty reactive in their metallic bonds. So it allows them to lose electrons easily. The simplest theory to understand is kind of little islands of cations with a sea of electrons surrounding it. So it's an electron sea. And all the valence electrons are shared by all of the metal cations. There is an organization, and the electrons are what we call delocalized throughout, meaning the electrons are interacting with all of the ions, not just stuck with one sodium. So that's what we mean by delocalized. And the bonding results in that all of the electrons are delocalized, and that actually explains a lot of things. One, it explains why metals conduct electricity. Conducts electricity because the electrons are delocalized. So it's easy for it to conduct other electrons because the electrons aren't stuck on one atom. It explains the fact that our metals have high melting points and all have very high boiling points. And we see that all of our solids, except for mercury, all of our metals are solid at room temperature. Mercury is weird. Mercury is a liquid at room temperature. But this big attraction between all of that sea of electrons is what gives them really high melting and boiling points. It also explains why they conduct heat and electricity because of that sea of electrons. Electricity can be conducted really easily with that sea of electrons, and because the electrons are just floating around in that sea and not stuck on one atom, that means that with heat, they can move more. And the more that they move, the more heat that's given off. So that also explains why they conduct heat very well. Also, it explains why they're easy to move, they're malleable, and they're ductile. And lastly, the sea of electrons explains why they reflect light. Because the electrons are just hanging out in the sea, that means if light hits it, an electron can be removed really easily. So it can reflect the light really easily. So that's really all we're going to talk about, our metallic bonds. And that's it for the material we're going to cover in the class. So now I have a quiz for you, because I wanted to finish the material. And don't forget, review tomorrow. So please put everything away. You don't need to talk to do that.